All right, so welcome to the first video for chemistry this year. This video is going to kind of cover and recap what we've been doing in chemistry for chapter 1 and then start into the information for chapter 2. So chapter 1 notes how is chemistry essential to our lives. We do have 5 main branches of chemistry. The first one that we deal with is organic, and organic chemistry has within it um, most carbon-containing compounds. So these are your gasoline, alcohols, any of those sorts of things, your plastics, pharmaceuticals. We do not get into much organic chemistry in this class, nor do we get into very much of it even in AP Chem. So that's something for a much more advanced college course. We do talk in here about inorganic chemistry, so that's matter that doesn't contain actually carbon-hydrogen bonds is what organic is. So it's stuff that doesn't have carbon-hydrogen bonds. We do talk about some metals, we talk about nonmetals, we talk about semiconductors. We do discuss physical chemistry in here, nature, matter changes, energy changes, reaction rates. We don't really get into much with mechanisms until you get into AP. Analytical chemistry then is components and composition of certain substances. So we touch very briefly on that. What you would study on that if you were a chemist would be food nutrients, quality control. And then there's biochemistry, which if you end up taking AP Bio, will be fundamental for that course, and they'll go much deeper into that. Regular or honors biology goes into some of this, as well as regular biology. They talk about fermentation in terms of anaerobic respiration. They talk about uh, respiration, photosynthesis, that sort of thing. So we do use the scientific method in here, systematic approach to problem solving. You're going to make an observation. You're going to state a problem, develop a hypothesis, which is generally considered to be an if-then statement. If this happens, then this will occur. Design, perform an experiment to test the hypothesis. You analyze your data, develop a conclusion related to it, and then if the hypothesis isn't valid, you would refine that and then repeat the experiment. Data collection is generally considered to happen in 2 phases or 2 different types, general categories. One of those is quantitative. The root word of that is quantity, meaning that you're going to have some sort of number that's going to be associated with that observation. Qualitative then deals with qualities. So, what of the 5 senses would you use to be able to describe what happened in that reaction? Smells bad, it looks purple, those sorts of things. Theory versus law then. Theory is when an experiment has been tested many times, it's accepted by the masses, they consider it a theory. So an explanation or an observation for a series of things. Theory of evolution is supported by natural selection. So we can't go back and prove that natural selection occurred necessarily, from one animal species to the next. But we've got a pretty good theory based on what we've seen in organisms that have very short lifespans, such as bacteria, where we can see that natural selection occurring just within that small population that has a very short life cycle. So that's a theory, though. We haven't actually seen it happen. Laws then are a statement, scientific principle, clear explanation. We know that it's happening. So, like the law of universal gravitation, you drop your pencil, it falls to the ground. All right, so that kind of sums up chapter 1. Chapter 2 then looks at how we use and analyze data, how we collect that. So first of all, we're going to talk about temperature scales. We have Kelvin is the temperature scale that's accepted by the metric system, and Kelvin is not in degrees. So Kelvin is where all molecular movement stops, is at 0 Kelvin. Water freezes at 273 Kelvin and it boils at 373 Kelvin. I will give you that 0 degrees Celsius equals 273 Kelvin. That will be on your test, that conversion factor. So you don't have to memorize that because it'll be given to you, but you are going to have to convert between Kelvin and Celsius using a calculator and that conversion factor. Celsius is typically what we will end up using in our labs this year. We use temperature probes, and those temperature probes can be converted to read in Kelvin for you if we do have a lab that does that, but most of the time we just collect in Celsius. I do have the Fahrenheit to Celsius formulas. You can see that they're kind of messy and icky to use. We don't use those in here. There's just no sense in it. We don't have any need for it, but you get an idea of where these temperatures are when you look at Fahrenheit, since that's what we're kind of comfortable in conversing with. So for boiling water, that's 212 Fahrenheit, that's 100 degrees Celsius, and it's 373 Kelvin. Freezing water then is 32 degrees Celsius, 32 degrees Fahrenheit, 0 Celsius, and 273 Kelvin. If we talk about absolute zero, that's going to occur at negative 460 Fahrenheit, negative 273 Celsius, and that would be our 0 point for Kelvin. We do have metric system. We kind of call it the metric system. It's the System International des Units. And trust me, my French is very poor, so I apologize for kind of slaughtering that. It is easier to use. It's based on powers of 10. If you flip back here and just look at the Celsius scale, it's much easier to remember that it boils at 100 and it freezes at 0 than to try to remember 212 and 32. So it's a much nicer, easier system to work with, especially since it's in the base 10. The entire industrialized world uses it except for the United States, but we're just stubborn and haven't been able to switch over and get to it. Base units for the metric system, for time, it's going to be seconds. Length is going to be meters. Mass is grams. Temperature, again, is Kelvin, but we tend to use degrees Celsius. And then we will be talking about something called a mole this year, and we'll get into that in much more detail, and that's the amount of a substance. We're going to measure that in moles. We have prefixes for these base units. We generally work within the mega, giga, mega, kilo. Here's our base unit. We have deci, centi, milli. Sometimes we go to micro. Nano is pretty common when we get into chapter 5 and are dealing with wavelengths and frequencies. Pico occasionally, and then we don't ever get this low, that small into any of our measurements. Density, then, we've been talking about that in terms of lab, ratio of mass of an object over volume. We're going to measure our mass in grams. Our volume is generally measured in milliliters, or it can also be measured in cubic centimeters. And it just so happens that 1 milliliter equals 1 centimeter cubed. We can talk in terms of accuracy and precision. So a lot of times people use these words interchangeably. They're not really supposed to be used interchangeably. Accuracy means how close you are to an accepted value. So for example, water at room temperature is supposed to have a density of 1 gram per milliliter. That would be the accepted value. If in lab, though, you ended up getting all of your values clustered together, and let's say that your density was 0.85, 0.84, 0.83 grams per milliliter, they would be very precise because they're all clustered together. They would be very precise there, but they wouldn't be very accurate. Accurate would mean that they were at 1 gram per milliliter or awfully darn close, and that would not be that way. So you're hoping that your results, whenever you do, several repeats of an experiment, are going to be both accurate and precise. And you can kind of see from these bullseyes what they're talking about. So this data would not be accurate or precise, nor would this. This would be very precise, but not accurate. And this would be both accurate and precise. All right, density and precision then. So if we're looking at some data here that is given to us, we can see that they're telling us that the accepted density for this substance is going to be 1.59 grams per milliliter. So they're asking you here which student is most precise. So we're going to see which students' values are clustered the closest together. So what do you think? Do you think it would be student A, student B, or student C? And if you look at the data, you can see that these values are clustered very close together. They're 1.7 is kind of in the middle of these two values here. And you can see that they were hitting that value every time. So that student's work was very precise. But this is the accepted value. That was not a very accurate value to come up with, considering that this is where you're supposed to be. So if we were looking to see which student was the most accurate, stating that student A was the most accurate would be the correct. Even though they're not quite as precise, their values aren't spot on like they were here, very close together. They're not spot on in terms of making sure that they were close to the value that they were supposed to have. So this student, you would want to use their data because it's much more close to the accepted value. All right, so scientific notation then is what we're going to be using this year to be able to get proper number of digits when we have an answer. And we'll get into more of that when we get into something called significant figures in the next few days. It also helps us to write really big numbers in a smaller space, and it's easier to kind of look and see what those numbers are without getting bogged down with too many zeros and that sort of thing. So when you're expressing things in scientific notation, you need to have a number between 1 and 9. And then you're also going to have it where it's multiplied by something and have 10 raised to a power or an exponent. So here's an example of scientific notation. Here we have the number 1,000. What you're doing is you're trying to get a number alone by itself that is between 1 and 9. So right now, we would assume that our decimal point, since it isn't written in for us, we would assume that that decimal point is right here. You need to count how many times you need to move that decimal point to get the number that you have between 1 and 9. And then you need to count how many spaces you move and know which direction you're going. So if you're going to the left, that value is going to be positive. If you have to move the decimal point to the right, then that value that 10 is raised to is going to be a negative value. So here for 1,000, you're going to count how many spaces we're going to the left. So we would go 1, 2, 3. By moving the decimal point here, that makes this number between 1 and 9. So that would be 1 times 10 to the third because we moved 2 places to the left. So a positive value, we move 3 spaces. Here our decimal point is in front of that value, so we're going to have to move it to the right, and we're going to count how many spaces we need to move it in order to get that value between 1 and 9. So I'm going to move it 1, 2, 3 spots, but this time I moved it to the right. So this time it's going to be 10 raised to the negative third. So here on this slide, I have some practice problems for you. Pause the video and see if you can come up with the correct answer for these. All right, welcome back. Hopefully you were able to obtain these values for your answer. This one here should be raised to the 5th power. I apologize for that. Let's get that corrected for you. There we go. All right, so that is scientific notation. Hopefully you were able to use your calculators and be able to get these values that you should have obtained. One last thing that we need to talk about today is percent error. Percent error is a ratio of how much of an error there is in your experiment based on accepted values. So out in the world, there's all kinds of accepted values that really smart chemists have come up with over the years. and we looked to those values to see how close our experiment was. So it doesn't matter whether the experimental value is larger or smaller than the accepted value, it's only the size of the error. So you're calculating an absolute value. So when you calculate percent error, you do that. And remember, absolute value is the distance from zero. You're hoping, what you're really hoping for when you do an experiment is that your experimental error is zero. That's what your goal is to have 0% error. So the further you are away from zero, the worse your experiment went. So here's an example of a problem that was done in lab. We had 4 degrees Celsius, and the experimental density of water then is 1 gram per milliliter. Lucille experimentally found the density of water to be 1.08. They want to know what her percent error is. So pause the video, use the formula from the last screen, and see if you can calculate the percent error. So you should have been able to find from this experiment that her experimental value was 1.08. We're going to subtract that from 1, which is our accepted value, and we're going to divide it by 1. Generally speaking, when I set these up, I put whatever the larger value is here minus the smaller value. Since it's distance from 0, it doesn't matter which one comes first, as long as you have the accepted value down in the bottom. Then you multiply it by 100, and for this case, you would end up with 8%. So that does our video for part 1 for our chapter 2 notes.